Uh, okay, so in this lecture, I wanted to discuss I wanted to discuss a couple of things, but for example, theory of Cartier duality, the general theory of Cartier duality between certain group ind-schemes and certain group schemes. So maybe the first thing I should say is that right. So this was so let me just say Cartier duality. First thing I should say is that this has also been worked out by Dima Rinkin and Joshua Munninger for different reasons. But so this came up sort of naturally in our project, and maybe at the end I can say a little bit about how it came. Right. So let me get started. So first, I want to start with the following. So first, let me suppose suppose I have a base field. Um, and okay, so let's consider the following. So let's consider a well, P over P. That means P is equipped with a co-multiplication, which is co-associative and co-unit. Okay, so the following construction. So the following construction. So given C, we can produce a functor. We can use this to produce a functor from K algebras to sets. So have a functor. Which I'll call F sub C from the category of K algebras to the category of sets. And it's defined by the following formula. Okay, so if R is a K algebra, I'll get sent to F sub C of R, and this is defined to be the collection of group-like elements in R tensor over K. So let me just define what this means. So here, well, first of all, I consider R tensor over K with C. So C is a coalgebra over R. Sorry, C is a coalgebra over K. So if I extend scalars, I get a coalgebra over R. So this is a coalgebra for R. And two is that, right, so in general, if we have a coalgebra, we'll say that an element is group-like. So we'll say that an element X of a coalgebra is group-like. If delta of X equals X tensor X, and if the co-unit of X okay. It was it's a co-unit. Okay, so whenever you have a co-unit of coalgebra, this what is eta? Eta is the map. So eta is the co-unit from the coalgebra to the base.
And sometimes it helps to pass from coalgebras to algebras.
Yes.
Which look more familiar to us. It's an innocent operation, at least in the finite dimension.
Yeah. Okay, so an example of this, suppose C is finite dimensional. Okay. So then we can describe this operation. Then we can describe that this is equivalent to the following. So then we can form the linear dual C dual. And because C is a coalgebra, that makes C dual into an algebra. C dual is a K algebra. And well, so R tensor with C is the same as K linear maps from C dual into R. And then this condition of being group-like translates the fact that a map is a homomorphism. Okay, so then, and okay, so F sub C of R is co-representable, namely its homomorphisms, K algebra homomorphisms from right, so from C dual. So if you have finite dimensional algebra, then this is basically spec of a finite dimension. Okay, so the example. But if C is not finite dimensional, well, there's the following theorem. So over a field, a co-commutative coalgebra is the union, it's the increasing union of finite dimensional subcoalgebras. So this is a basic feature of coalgebras over fields. And so what this means is that, well, so this construction that carries C to F sub C, it commutes with filtered colimits at C. So this means that for any C, so corollary is that for any coalgebra C, coalgebra C over K, which again is a field, F sub C as a functor is an infinite scheme, is a filtered colimit filtered colimit of finite case. So in fact, we can say more precisely, what we get is actually an equivalence of categories. So in fact, we get an equivalence. So we get an equivalence of categories between the one hand commutative algebras and ind of finite schemes. We can think of this, so this is going to be a subcategory of just functors from K algebras into sets.
And when you write int of finite schemes, you mean the category of int objects associated to finite schemes. Those embeddings.
Okay, so I'm just saying it's an equivalence of categories, so they don't have to be closed embeddings. But right, so I guess if you have an ind object, I think because you're working, everything is finite dimensional, you may as well assume that all the transition maps are closed embeddings. So if you think of it as an ind system, you may as well, yeah.
Finite affine schemes?
Well, I guess I think finite will include affine.
So finite is only affine.
Yeah, so a finite map is always required to be.
I guess you already said this, but for you, is the coalgebra always co-augmented?
Yes. Yeah, so that corresponds, when you dualize, that corresponds to having a unit.
And that's just convention for the rest of today.
Sure. Okay, so you get this description of co-commutative coalgebras over K as a full subcategory, well, either as this or equivalently as a full subcategory of functors on K algebras. And so you have some natural examples. So for example, something like the formal affine line or formal affine space, and that's going to be in here. And so it corresponds to a coalgebra, which will be some sort of divided power. Maybe I should even write that. Like that. So an example is that you have the say the divided power coalgebra. So this is a coalgebra over K with a basis on X is 2 such that the co-multiplication of 1x phi is the sum for a plus b equals phi of x of a. So as an example, you have this divided power coalgebra. And the dual, so on the other side, this corresponds to the formula affine line. So this corresponds to A1 hat. It's the functor sending R to its galvanic. Okay.
So A1 hat is the functor which takes an array R to the set of its node.
Yes, the set of its input. So I guess I wanted to explain a generalization of this where K is allowed to be a more general array. So explain. Arbitrary rings. That's my goal for today, first of all. Maybe I could say a little bit about one other category that both of these are related to, which maybe will clarify this result and clarify this sort of fundamental theorem of coalgebras. Okay, so a remark is that, so maybe before I start the goal, let me say that a remark is that, so in this core layer, we have a correspondence between these coalgebras and infinite schemes. So there's a third category, which is equivalent to both of them. And the third category is going to be a category of topological rings. So the third category equivalent to both. So namely, I'm going to consider topological K-algebras. So consider topological K-algebras, which I'll call A, which have the following properties. So, right. So I want to assume that first of all, A is complete. So A has a neighborhood basis as a neighborhood basis at the origin of K vector spaces, K vector subspaces. K vector subspaces, let's call them J sub alpha. And which are of finite codimension. It's going to be a topological K algebra which has this.
And the basis means the base of neighborhoods of C.
Basis of neighborhoods of at zero. And furthermore, A is two. So the idea is that if we have one of these topological K algebras, we can produce a functor, or we can produce, well, on the one hand, okay, so let me explain why how this is related to both of the categories over here. And so by the way, I should say that an example of such an A could be something like K double brackets T. So we could take K double brackets T with the T-adic topology, but we could also consider this ring that, so came up in some of the earlier talks. So namely, this is the sort of divided power version of this. So I'll write this as K double brackets T to the I over I factorial for all I greater than or equal to 0. So this is sort of all infinite series in expressions T to the I over I factorial. And well, this also has a neighborhood basis at 0. I mean, this is given the natural topology, the natural sort of product neighborhood basis at 0 is all power series that start with T to the N, will start in degree at least 10. So I'm just pointing this out because it's a topology, it's a K-linear topology that satisfies these conditions, but it's not an adic topology.
So in fact, your properties 1 and 2 are properties of A as a topological vector. They have nothing to do with application. So, and so the reason why this category is equivalent category of coalgebras is also purely linear, so to say. It's because if you consider the category of topological vector spaces satisfying these two conditions, then it's due to the category of abstract discrete vector spaces.
Yes.
And this anti-equivalence, which is the usual functor of duality. In a discrete vector space, you can consider all linear functions, the space of all linear functions on it, and then you get a topological space satisfying these two properties. And conversely, if you have a topological vector properties 1 and 2, then space of continuous functionals in it is a vector space. These are the two functions.
So thank you for your comment. So maybe let me actually write that down because it also would be useful. So let me, so I think, in fact, okay, so let me put this remark on pause for a second and explain and emphasize in fact, because this is also going to come back for so in fact, we're using some sort of basic topological duality. So we're using some sort of topological duality. So we have a duality between, we don't say algebras and coalgebras everywhere, we just have a linear duality. So the linear duality is between, okay, so on the one hand, we have all just plain K vector spaces. And on the other hand, we have topological K vector spaces. Spaces W, which have the property that W has a neighborhood basis, the same thing, neighborhood basis of finite codimensional subspaces. And is complete. And so this is coming from duality. If you have a discrete vector space, you take its topological dual, sort of dual space topology. Okay, and sort of. Okay, so we have this linear duality, and then the idea is that this linear duality, well, it'll interchange algebras and coalgebras. So this linear duality will imply essentially this the duality of sorry. So maybe so if we go back over here, So the idea is that this class of topological K-algebras, which have these properties by this linear duality, is anti-equivalent to coalgebras. So just from this sort of linear duality, you get an anti-equivalence between co-commutative coalgebras and topological K-algebras that have this property. So now the last thing to say, and okay, maybe I start a new board. So the last thing to say is that if you have such a topological algebra, so given such a topological algebra A, you get a functor from K-algebras to sets by taking continuous homomorphisms out of it. So you get a functor from K-algebras to sets sends R to continuous homomorphisms from A and T. And, well, basically there's a small additional observation here, which is equivalent to this fundamental theorem of coalgebras. But the small further observation is that A actually has a neighborhood basis, not only of subspaces, but of ideals. So under these conditions, so as stated, A was given a K-linear topology, and the condition of the topology was only defined in terms of its as a subspace, but in fact it has a neighborhood basis in terms of ideals. A neighborhood basis of ideals of finite codimension of J alpha. And so then what you get is that this functor is in fact an infinite scheme. So it's just a colimit of Homs, K algebra Homs, from A mod J alpha. So small additional observation is that if you have a topological K algebra with these properties, then it automatically has not only a K, like a basis of a basis of a vector space, but it has actually a neighborhood basis of ideals. So I think this is more or less equivalent to this fundamental theorem of coalgebras.
And I vaguely remember that, for instance, for topological algebras, not again for some supporters. If I remember right, this is not true, and there are some obvious properties.
Okay, shall I just explain this briefly?
Yes.
Okay, so what is the proof? So, okay, so proof of proof that A admits neighborhood basis of ideals okay, so choose some open K subspace. Let's call it n sub alpha. So what we need to do is it's enough to produce so it's enough to produce an open K subspace and beta such that A times n beta is contained in n. Okay, so it's enough to show that you have a neighborhood basis of ideals, and so it's enough. So you have a neighborhood basis of k subspaces. You could try to make them into ideals by multiplying them by A, but then you have to show that it sort of converges to 0. All right. So I think the first step is so there exists beta 1 such that n sub beta 1 times n sub beta 1 is contained in alpha. And that's because of continuity. That's by continuity of multiplication. But we also know that n sub beta 1, so this is an open neighborhood, so it has finite codimension. There also exists, so there exists, let's say, x1 through x sub m, A, such that A is equal to n sub beta 1 plus the span of x1 through x. So we can do this, but this implies right. So now we can find a beta which is greater than or equal to beta 1, such that let's see, so n sub beta times x sub I is contained in n sub alpha. This is again by continuity of multiplication. Okay, so then if you combine these, what you get is that n sub beta times A is equal to n sub beta times n sub beta 1 plus the span of x1. And now, by assumption, beta is greater than or equal to beta 1. So the first term is contained in n sub alpha, and also the second thing is contained in n alpha. So that's so basically you just use the fact that all the neighborhoods are finite codimension. Okay, so any questions? So by the way, I think this is more or less equivalent to, this is sort of reproving this fundamental theorem of coalgebras, which I think I found the proof a little hard. Some of the proofs of the fundamental theorem of coalgebras, well, I found this a little bit easier to understand than some of the okay. So all right, maybe I should move on. All right, so I wanted to explain how this generalizes to arbitrary commutative rings. And right, so I guess maybe the starting point is so we want to do this for arbitrary commutative rings, and in that case the idea is, well, we can still talk about co-commutative coalgebras, and so let me explain that. Cool.
Just one. So I think I'm not, as I said, I vaguely remember that for the algebras correspondence, not true. And I think the counterexample is the algebra of vector fields on a formal disk. So I'm tired and I'm not sure that way. But again, if somebody wants to understand the details, it's better to think about the algebras, at least for amusement, and maybe to find out whether this example is indeed a context.
So the goal is to have something like this for arbitrary k. Right. So maybe I should start by first explaining the theory of linear duality in this context, and then we'll get to the statement for algebras. Okay, so there's an analog of this linear duality. So now let k be any commutative. So I guess this is a thing. Yes, I think mostly due to by knowing Poisson. So Jay said there's a correspondence between the following different types of problems. There is a possibly empty equivalence. So on the one hand, we're going to consider countably generated projective K modules. So we revealed the great simplification is that everything is free. And so for arbitrary K, it seems that a natural thing is to consider countably generated projective modules. So countably So we'll consider coalgebras that are of this form. Okay, so the next thing is going to be yes. Okay, thank you. Okay, so next we're going to have complete topological K modules. Call it M, which have the following properties. So such that M has a countable basis. At 0. Call it M sub n. And moreover, we'll have some conditions. So the first condition is that all the quotients n mod m sub n are finite.
Just a moment. There are two slightly different ways of using the word basis. There is a notion of basis of a vector space. There is a notion of base of neighborhoods with zero. So when you are
Neighborhood basis.
maybe we can say basis in one case and base in another, or at least so there is a danger.
Countable base. Okay, and so now we'll need some conditions. So so we got the idea. So this is just going to be linear duality. You have a module and you take its dual with the natural topology. And the conditions are okay. So all of these things are finitely generated. Well, I'm sorry. Maybe and so I'm sorry. And so the condition is going to be that the pro system M mod M sub n is pro equivalent to a tower of finite Fourier modules. So maybe I'm so this is strictly not necessary. Such that and the pro system M mod M sub n is pro equivalent to a tower of finite free K modules.
Excuse me. And suppose that you start with just your projective model in one is finitely generated itself. Then here you will get just one projective model. Yes, it's dual. And why it would be tower of free?
Sorry, so I think then sorry, because then so if you have right, so the question is if you have just a finitely generated projective module, then okay, so then the construction should be you take the dual and it should be the constant pro system. But I think so if you have a finitely generated projective module, it's a direct summand of a free module
Fine, you will.
via some projector, and then you take the pro system of that projector.
But then you cannot write M mod M M. Maybe the maybe the condition is that it's equivalent to a project. Just a moment. To a projective to a system of projective system of finitely generated free modules, but they are not quotients of M in general. They are just abstract. In this example, you wrote your process.
So I said that there's
I see. So the system of quotients, the pro system of quotients, is equivalent to a tower of finite free modules in which the transition maps are not required to be projected. This is the trick.
Right, so it's important, right? So this is a tower of finite free K modules. The maps are not required to be surjective, but they will satisfy because right, so being surjective, I mean this is all a condition at the level of pro systems, and being surjective is not a condition at the level of pro systems, but this Mittag-Leffler condition is a condition at the level of pro systems. So you'll have the Mittag-Leffler condition.
Okay, so first of all, the first piece of integration information is the notion of pro object, or for instance, an object is important and not quite obvious. And probably there is a place where you can read about it. I think this was an appendix in some, maybe in EGF volume 1. So there is something which has to be understood slowly if you want to understand. Second, there is this observation that if you have, let's say, a finitely generated projective module, then it can be represented as a, say, projective limit for three finitely generated three modules, and the way explained by Q, presented as a direct summons, precisely as an image of a projector I acting on a free finitely generated free. Then you take a very stupid projective system where all the terms are, each term is this finitely generated free modules, and each transition map is pi. And not only it's a projective limit, but moreover, you have an equivalent, an isomorphism of processes. So that's on one hand the constant process projective system formed by our finitely generated models, and on the other hand you have the projective system of free models. The transition maps are given by our projectors, and these projectives, the pro objects are this is one observation to keep in your subconscious. So also, maybe another thing to keep in mind is, for instance, that not in general, not every projective, or not every countably generated projective modules is a direct sum of finitely generated. I don't remember a counter example, but there exists such example exists. And this is at least one of the reasons why the formulation of the theorem is a little bit complicated.
Can I just say one more comment about this theorem? Yeah, so this is maybe not how it was originally formulated. Let me just explain the relation with okay, so right. So maybe also just to go back again, the idea is that you send P to its linear dual, and in particular, right, so in particular, if you have a free module, then this is completely the same as over a field, but then it's basically you extend it to projective modules by taking idempotent completion. Now let me explain the characterization, but the fact that this is actually an equivalence is a serious theorem. And so let me just explain what goes into it.
Yes, and countability is important.
Yes, in particular, yeah. So right, another comment is that so it'll be important to use this notion of pro objects and ind objects, but I think only sequential pro objects are really important for this. So the remark is that okay. So first of all, there's a theorem of Lazard. Any flat module is a filtered colimit of finite free modules. And if it's countably generated, then you can arrange it to be a sequential colimit. So if countably generated, I take a sequential colimit. And two, so now this is the theorem of Raynaud and Brisson. So theorem, I mean, so they actually prove something more general, but let's just say it in the countable case. So given a sequence of finite free modules, n1, n2, 3, a dot, then you can form the colimit, and the colimit is some flat module. And then the statement is that the colimit, n, is the colimit of the m sub i's, is projective if and only if, when you dualize and you form the pro system of their duals, that satisfies the Mittag-Leffler condition, which is the same as saying it's pro equivalent to something which comes from a complete topological module. So the n sub I dual satisfy the Mittag-Leffler condition. In other words, the images stabilize, or equivalent to saying that it's pro-equivalent to a tower of surjections. Okay, and a tower of surjections, you think of a tower of surjections as a pro-object, that's just the same thing as a complete topological module, which has which has a countable basis of submodules. So this is a theorem that Raynaud and Brisson proved about when if you have flatness, when you get projectivity, and then serves it's this Mittag-Leffler condition in the countable case. Okay. So that's the linear algebra statement. And
Yes, and countability assumptions are here for two different reasons. Number one, that this is enough for us and for most purposes. And number two, without countability assumptions, the statement become wrong if understood later.
So here we really need countability.
So are you saying that theorem is equivalent to the second statement? So you
Yeah, the
have
theorem is basically the second statement. Okay, so this is an anti-equivalence of categories given by duality, and it also respects tensor products. So you get an equivalence between coalgebras and algebras. And you can make a similar argument as in the one that I just erased, apparently. So let me just formulate the theorem. So okay, so the theorem, right, and so again, I should say this was also proved by Ringkin and Manager, and I guess this statement was also suggested to us by Volodia. The statement is that, okay, so again, K is any ring, so you have, so you have an, that's right, so you have an equivalence between the following two categories. Okay, so first of all, you have so K coalgebra C such that the underlying K module is countably generated and projected. And two is going to be, well, a certain class of ind-schemes. So let's say infinite schemes, which are, again, they're going to be sequential. So the diagrams, x1, maybe let me write it this way. So spec R1 maps to spec R2 maps to the top. And the condition, well, the condition is that, right, so let's see. So the condition is that the tower, so if you have a sequential ind-scheme, that's a sequential column of infinite schemes, so it's a sequential column of finite algebras, which we can think of as a tower of K algebras, such that the tower, so the tower of one is a map from R2 receiving a map. Well, such that this tower, as a tower of K modules, well, it's equivalent to so it's equivalent to that. So it's equivalent to a tower of finite free K modules satisfying the integral. Okay, and three is going to be complete topological K algebras which have a countable basis at 0 and such that the tower of those quotients again have this property. So with countable basis, it's called an I sub n, such that the tower A mod I sub n is pro-equivalent to a tower of finite free K modules. Okay. So this is basically right. So now I think it's basically a consequence of this of the theorem, the statement at the level of modules, when you dualize, when you turn algebras into coalgebras, and also keeping in mind, well, this argument that I mentioned, that if you have an algebra, you have a topological algebra, which satisfies these kinds of conditions, you automatically have a basis of ideals. You automatically have a neighborhood basis of ideals, and that's why you can think of it as literally a tower of algebras.
So in property 3, the condition for the INs is purely formulated in just linear terms.
Yes.
But then you are saying that automatically there is another such sequence
Of ideals.
which is formed by this.
And that's by the same argument that we did for a field. Yeah, so in particular, this, right, so the comment is that, well, you're considering some sort of topological K-algebras. So how do you get these kinds of topological K-algebras? You could imagine that you have just an ordinary algebra, and you have some collection of ideals. You have a descending set of ideals, say a descending sequence of ideals, and you can form the completion with respect to that topology. So that might be an example of this when you form the completion, but then it's not sort of arbitrary. There's sort of a flatness condition. And the flatness condition is purely module theoretic. The module theoretic flatness condition is that the sequence is equivalent to, as a pro system, it's equivalent to a tower of finite free K modules.
So this is not the naive requirement of the algebra being flat. It's kind of Pickwickian flatness.
Yeah. So right. So thanks. So
it's flat. So each Ri is not required to be flat.
Right. So yeah. So in particular, thank you. So
it somehow becomes flat in the limit, but not flat in the inclusion, which makes sense, and not even flat in some topological sense. No, it's rather flatness in the sense of process.
Yes. Right. So maybe I should just say, right. So the difference, yes. So thank you. The difference between this and the case where K is a field, when you have a field, you have this fundamental theorem of coalgebras, which sort of simplifies things a lot. And this is sort of supposed to be some replacement of that, I think. But in particular, if you have a coalgebra, you can certainly produce an ind-scheme, infinite scheme by doing the same construction. But it's going to be some filtered column of finite schemes. But it's not clear that you can arrange it to be a filtered column of finite flat schemes. But instead, what you get, so these individual, so again, the construction from 1 to 2 is, again, you send C to this primitive construction, and it's an ind-scheme. But these individual terms might not be finite flat. In fact, the individual terms are not really well defined a priori. So it's not clear that if you have something as in 2, it's not clear that you can arrange this to be an ind system where all the R sub i's are individually flat. The statement is only that when you think of it as a tower of modules, you can make it.
And there are examples when it's indeed impossible.
Actually, do you have an example?
Powers is an example.
But I thought divided powers, you can, if you mod out by everything in degree of least n, that's a finite free module. Actually, I would be interested if.
Examples at least for the non-linear story. So for coalgebras, let's say, because there are non-trivial, for instance, there are non. So here let me violate the promise to be independent from the previous talks. So in the previous talks, we considered W hat torsions. Now one can ask whether hat torsors over some base. Suppose let's fix K. Let's fix a ring K, and let us ask whether all K are trivial. And in general, the answer is no. namely, it's no, for instance, it's spec K is semi-cubic. And then I think the same. Well, I'm not 100% sure, but I think the same example which shows that there are non-trivial torsos over it gives you a counterexample. Shows that the corresponding ind-scheme, I think, is not union of flat, finite flat subscheme. It's just infinite, but not. Again,
I'd be very
I thought
interested in
about
checking
these
that.
questions long ago,
Okay,
but I think the same counterexample works.
well, I would love to understand. Yeah, so maybe a related comment is that this condition is local in the flat topology on K, but I think having, like, actually writing an n system of finite consequences, not saying. Okay, well, thank you for the comment. So, well, maybe I should explain the version for, just explain the consequence for group schemes, and then maybe it's a good time for a break.
And at some point we need a break.
I was gonna say, yeah, right after I explain this group scheme, what the group schemes. Sorry, so I just explained everything for coalgebras and ind-schemes, but then you can, I mean, it's compatible with products, so you can add a group structure. So more or less a corollary of this is okay. So if you add a group structure over here, that corresponds to adding an algebra structure on the coalgebra. So just corollary. So corollary of this is that you have a correspondence between okay. So this commutative, co-commutative hot elements for K whose underlying K module is countable underlying I think hop because it's already a coalgebra and then you're adding an algebra structure.
Yeah, but like you need you want the algebra structure to be like right, not the co-algebra structure, because you're taking spec of the opposite, like spec of the dual.
I think I want everything to be commutative. Sorry, I'm not sure if that's.
No, I mean like
Just on, are these Hopf algebras discrete here?
Yes, discrete.
So this, of course, in the definition of Hopf algebras, algebra structure and coalgebra structure rules, but here to relate this to the previous story, we think of these Hopf algebras as co-algebras with an additional structure.
Yes. And second, group ind-schemes. Ind-schemes G over K, which have the following property, such that the underlying ind-scheme, well, it's as in two. So it's infinite. Well, it's such that the underlying pro ring such that underlying pro ring or the underlying pro module yeah, so it satisfies basically this kind of flatness condition. So it's pro equivalent to tower of finite freeze, satisfying the metacognition. So I think for at least for the applications that we were considering, maybe for many of them, K is like maybe an Artinian ring. So the Mittag-Leffler condition is automatic for an Artinian ring. So then the content is really that you have some sort of flatness. So that G as a group in scheme over this Artinian ring is flat, again, in some sort of funny sense, because it's not literally, a priori, it's not literally a colimit of flat, or it might not be a colimit of flat case space. Okay, and so then just the example, I'll stop.
I'm sorry, Akil, but in the corollary, it should be commutative group in schemes.
Thank you. Commutative. Thank you very much.
But just a moment. The Hopf algebras are required to be both commutative and commutative. But of course, there is a similar corollary for arbitrary in schemes if the Hopf algebras are not required to be.
Okay. So let me just give one example. So this is the kind of Cartier duality that came up in our project. An example was that let's see. So in part one. So in particular, part one, these are right. So these are just commutative group schemes. So in particular, these give you classical. The idea is that this gives you classical commutative group schemes, which satisfy this projectivity condition. But an example is right. So it's this group scheme x plus y plus q. So it's a group law given by x comma y goes to x plus y plus q minus 1 times xy, and this is over stuff of zp double brackets q minus 1. This is such a group scheme over this this q line. And on the other hand, you have the object that I guess Vadim and I spoke about in the previous lecture. So so basically the kernel. Okay, so this is one point where kernel of GM cross stuff ZP double brackets Q minus 1 to this sheared Kudaram stack of the pullback of the sheared prismatization of GM. So this was a natural group in scheme that came up in the previous a week ago. And well, the statement which explained or I mentioned last time, but now we can say more precisely, is that it's Cartier dual to this sort of simple classical group scheme. This over here, what you get is actually a group in scheme. Okay, so maybe one thing, maybe I say one more thing about Cartier consequence. So I guess this is still maybe a little bit tentative. Haven't checked everything very carefully, but possibly others sense more. So the statement is that you can also use this to describe quasi-co, and I think this is one of the main reasons you're interested in this. So so again, if we go back to this theorem, so if G is a group in scheme which is Cartier dual to an ordinary group, to let's say spec A, where A is a Hopf algebra. Well, then you get the statement that okay, so maybe I want to assume here that K is Noetherian. Hopefully, it's not necessary. That quasi-co of BG. So we can form BG as a stack. We can form quasi-co. The statement is that that's the same as modules of. So okay, so this is in particular, this is saying that representations of these group M schemes are the same as modules over. Okay, so maybe I'm already a little bit over time, so maybe we should take a break, and maybe after the break, I can talk. I was planning to talk a little bit more about this. So in particular, what in formulating all of these things, maybe something that's a little bit tricky is actually seeing that you have this kind of flatness condition, and like how does one check that you have this kind of thing? And I was thinking maybe after the break I can say a little bit more about flatness and some examples of it and how one can check it in practice. So
May I tell a funny story? How I came across this important paper by Renaud and Grissom. Yes, in fact, I knew about this paper, and many knew about this paper, but for different reasons. It's a long paper with a lot of important materials. And this is only one. So the story was that I was visiting America, more precisely Princeton then, and the mathematical science net was brand new. And somebody told me that you can search, you can type a word or collect several words in the field which is called anywhere. And once I typed the words Mittag-Leffler model, and the system immediately brought me to the paper by Renaud and Grissom, in which this notion was introduced. Now, I had some reasons to type these particular words because I was thinking about ind-schemes, and I realized that Mittag-Leffler condition could be important. But without the online version medical reviews, I wouldn't know how to find the people or the paper which could help me, or the people which could help. And this is how I found it. Another funny aspect is that this paper by Renaud and Grissom consists of two parts, and it seems that the author of one part was not quite aware of what is done in the other part. At least there seems to be cases where some references would be helpful on this. So anyway, life is the internet was used now.
I say maybe there's going to be a version of the story with ChatGPT replacing.
There's
going to be a version of the story soon with ChatGPT replacing MathSciNet.
I don't know.
Okay, so I want to just say something about flatness. And yeah, so just a comment is that so the role of so flatness is an important role in general in theory of prismatization. And so in this theory of sheared prismatization, well, often one's working with ind-schemes rather than schemes. And we were wondering for a while about having some analog of flatness in this context, in particular making certain arguments. So we came up with some definitions that would be very interested in any comments or suggestions. Okay, so so maybe just for motivation. So recall from the previous talk, we had this condition. Okay, so recall from first half. Given a tower of R modules, we might want to know for example, we might want to know when it's pro-equivalent to a tower of finite Friedland modules.
And when you say tower, this means countable projective system whose terms are labeled by.
So we might want to know when it's pro-equivalent to a tower of finite Friedland. So at least that's one. All right, so following definition. So let's say R is a commutative ring. and so let's say I have a pro system, and for this actually it doesn't need to be a sequential pro system, any system. This makes sense. So is a pro system R modules. So we're going to say that it's flat if the following holds. So the condition was that so for all R modules n, the pro system so for each m sub I can form the jth Tor group with m sub I, and the condition is that this pro system, as I varies, it's the pro system in I, and that this is pro zero for any j greater than zero.
So zero means what? Zero is a pro object.
Zero is a pro object. Okay.
Is it enough to require this for j equals 1?
I don't know.
Not clear.
Not clear. Yeah, okay. So let me write that as a question. Yeah. So question. Is it enough to require for j okay, but I have to think about it. Yeah, I just about it. But maybe let me also ask another question. So another question is it enough? So one way you could have something which is flat in the sense is if all the m sub i's are themselves flat, because then all of these Tor groups would just be zero. And so anything which is pro equivalent, so this is also really a condition on the pro system, not on the individual like sequence or indexing diagram. So the question is there a nice example? So an example of a pro system which is flat in this sense, but not pro equivalent to a diagram of flat modules. Okay, and so I think these questions are maybe related, because one comment is that if you have a pro system, if it's pro equivalent to a tower of flat modules, then you actually get something slightly stronger than this. Namely, you get sort of pro zero uniformly in all j greater than zero. So for example, the direct sum over all j greater than zero of these pro systems is also pro zero. But this is a slightly weaker condition. So okay, so this is your question. And I would hope or assume that the answer is that there is such an example, but we're not able to come up with one.
One question. So condition is that something should hold. So first of all, it's easier for me to think about sequential systems. Now, condition that the persistent is zero means that every element it's a condition of the type for every m there exists an m such that something m and n we have the condition that something should hold for any R module but each R module n will have this, and this existence requirement will give you something, will guarantee that something exists, but it will a priori depend capital.
But it has to be uniform.
However,
Yes.
if you have some R modules, you can form their direct subs, and this will give you some uniform. So I don't know how far you can move such cheap arguments, but so maybe you want to, maybe you there is a way to formulate it, at least for sequential projective system. What does the condition really mean?
Yes, so thanks. So that's so important that we're asking this for all our modules and not only say finally generated modules. So an equivalent formulation, which maybe it's better to look this way. So which is that the pro system of functors. The pro system of functors given by taking the jth tor with the m sub I, that is pro zero as it's a pro system of functors.
So in other words, that there's some kind of uniform estimate on the transition maps being zero, independent of the input n.
That's right. But it could depend on j. So so it's saying that tor j from m sub I, that these maps eventually become zero. So it's saying that so i.e. so fix j and fix I. So then there exists j prime greater than or equal to j, such that the map tor sorry, I messed it up. Sorry, just I prime greater than or equal to I, such that tor j of m sub I prime to tor j m sub I.
Is this a different definition from the one you
No, this is equivalent. This is just unwinding what it.
Equivalent
No,
for
sorry, I
cheap
mean-
reasons. Yes. It's equivalent for a simple reason.
Oh, sorry.
So between the functor one and the one where you're taking it.
Yes, but we're sort of cheap. Yeah, for the reason is that if it's true for each n, it must be true uniformly. Because it's not true, because it's closed under direct sums. It's for all modules n. So if you don't have uniformity, you could take some big direct sum. Okay.
You can also take just truncation, take just derived tensor product and truncate it. I think from it.
Yeah, so maybe I should formulate that. Maybe I should.
And this seems to be stronger.
Oh, sorry. Do
You can take derived tensor product and remove usual tensor product from it, just truncate it. You can ask if the thing will also be pro zero.
So I think this is equivalent to asking that for if you truncate in any finite range of dimensions.
Mhm.
Right. So actually that's something that we were wondering about. So great. So let me add that thing. Let me add that as a comment. So remark. This is also related to the question that I was asking. So maybe a remark. A stronger condition, but I think this is maybe not a condition that we would want to use. Well, at least I think that it may be harder to use. So a stronger condition is that the power. So so if you take let me again just use the sort of for any n. The pro system of, so let's topologically truncate. Prosystem. Sorry? So a stronger condition on the prosystem is that for any module n, any R module n, this prosystem here, now this is a prosystem in the derived category R, and that it's pro zero in the derived category.
We have question about previous definition. So, for individual modules rather than for product system, we know that if it's true for Tor1, then it's true. If Tor1 vanishes, then all higher vanish. Yes. And what is the explanation? For instance, how can you compute Tor2 between mi and n? You can choose a homomorphism from a free module to n. Then let n prime be its kernel. And then you can compare the tors with n and the tors with n prime. What is the relation?
I guess it's shifted. I guess it will be shifted.
It will be shifted. And if so, then why it's not? Why doesn't it prove that it's enough to check the condition for Tor1?
That sounds very reasonable. So
What?
that sounds very reasonable to me. So I think you're saying the answer to this question is yes. So sorry, I hadn't thought about this question before, but I think what you're saying sounds. Thank you. Okay, so for example, maybe just one comment is so the second question, if you had something which is pro-equivalent to a diagram of flat modules, then that will imply the stronger condition. So this is a stronger condition than the condition that I formulated up here of something being of a prosystem being flat. So so to answer this question, one answer to this question would be if there's an example where you have this, but you don't have, or I'm sorry, where you have flatness in the sense that I formulated, but not. Okay. Let me just make a small remark. Is that or extension of the definition? The definition, if R is now an animated ring.
But just is it shifted in the right direction or in the wrong direction? Or if you have this exact sequence 0 goes to n prime, goes to free model, goes to n, goes to 0, then
Comes Tor1.
Tor2 with n, Tor2 with n becomes Tor1 with n prime.
Yes,
So it is the right
right.
direction.
Okay, so if you have an animated ring, and if you have a prosystem, so if this is the prosystem, and so in the connective derived category, we'll say it's flat if for all R modules n, so here now these are classical R modules, well, the condition is that if we take the jth cohomology of n sub I derived tensor n, consider this as a prosystem I. This is pro zero.
I don't know. Again, for j greater than 0.
For j not, yeah, thank you. For any j. So this is just a generalization of the previous definition to prose system with the derived count. Okay, so let me just make a couple of remarks about this definition. So
But just to suppose R is a usual ring, for instance, then we can still consider prose systems of complexes. And then instead of D of R, the heart of D of R is just the category of term. In this case, Rn is just, okay, so in this case,
okay, so maybe I can make a couple of remarks about this definition, which was why I thought maybe this definition would be more convenient at variance. So remarks. So the first statement is that it's local in the flat topology. So, well, okay, one is that it's stable under base change. Stable under base change. R prime. Prose system over R, and it's flat in the sense that when you base change to R prime, it's flat. Okay. Second is that it descends under faithfully flat maps. So if you have a prose system over R and you base change it to R prime, then if it's flat over there, it's flat over R. So actually, that was the reason to use the definition that I explained and not the stronger condition. Because if you use the stronger condition, it's not clear, at least not clear to me.
just a moment. So these are the remarks about which of the definition?
So about the definition, well, about the definition of flatness then.
So this was just a digression. We return to the previous.
Sorry, what was it?
About animated stuff.
No, sorry. This is also. I mean, this is just an extension of the definition. This is just an extension of the definition in the animated.
So it's stable under any
base
change. In the sense under faith for the flat. And this is at least true for the original definition, but then you say that the motivation for this stronger, and then you said that this was
Sorry, so I was just saying that there's potentially a stronger condition that you could impose, which is this condition over here. And if you impose this stronger condition and use this as the definition of flatness, it's not clear to me that it would be local in the flat topology on R.
Okay, so let's forget. Okay,
sorry. The other thing is, okay, so now let me formulate something which works for, so one reason to introduce this is I want to formulate the next statement. So if M spy, so maybe to formulate it, I really need to use the wrong category. And say I sitting inside R is a nilpotent ideal. Then the statement is that this tower is flat if and only if it becomes flat after base change to R mod I. Flat over R mod. So you can sort of descend along a nilpotent ideal. This is an analog, a nilpotent criterion for flatness. Okay, and this is easy to prove. So All right. Okay, so okay, any questions about the definition? Or
Like the derived base change or?
you have to take the derived base change here. Otherwise, you can take like R mod I itself. Okay. So let me explain one reason that this definition can be useful. So so this is a definition. Okay, so a consequence is that you can use this to give some notion of an ind-scheme being flat. All right. So let me explain following proposition. So proposition, and to formulate this proposition, maybe it will be convenient to formulate it in this generality. But okay, so proposition. So let M sub I be a prosystem in D of R such that the M sub i's are almost perfect. Pseudo-coherent. So if R is a Cartier ring, that's the same as saying that all the homology modules are finitely generated. So uh, so okay, let me say this. So now the following are equivalent. So all right. So M sub I is flat in a sense. And two is that it satisfies the sort of okay. So after for any n, so for any n, if I take this pro system. So okay, so they're formulating this somewhat more generally, but maybe in the example we want, R is an Noetherian ring, and the M sub i's are just classical finitely generated modules. So the statement is that if it's a pro-system of pseudo-coherent objects, then being flat, which is this Tor condition, which in particular is local in the flat topology, is equivalent to saying that it's pro-equivalent to a system of finite free modules. So this was
Can you can you write the formulation of this particular case?
Sure. So let me explain the example and maybe let's catch the example.
And sorry, is the proposition only for Noetherian R?
No, the proposition is for any, I mean, actually for any animated ring.
But then is it almost perfect or pseudo-coherent in general?
Oh, I was using them to be the same. I was okay. I don't know if there's a different definition, but I was using pseudo-coherent to be almost perfect.
Okay, great.
So example, let's say R is a classical Noetherian ring. And let's say we have a sequence. Let's say we have a sequence. A sequence of the tower of finitely generated classical R modules. Okay, so then the following are equivalent. And yes, the following are equivalent. So one is that this is equivalent to a tower of finite free. And two is that the M sub i's are flat. So again, I think it was not clear to me that condition one is local in the flat topology, but condition two is local in the flat.
So I think your goal was to generalize so the prototype is the statement that we have the Arbitrary ring and a finite generated model, then its flatness is equivalent to projectivity.
So remark.
And you are trying to generalize this for projective systems.
Yes. Okay, so maybe this was useful for us because we wanted to, again, in our example, we had this group scheme, this group ind-scheme that showed up as a kernel of GM, mapping to this shared Q-to-ROM stack. And well, we wanted to show that it was Cartier dual to something. And in fact, the main thing in doing that is actually to show that it is an input to Cartier duality, meaning it satisfies this flatness condition. Because then, okay, so shall I sketch the proof of this result?
Thank you. It depends on the answer depends on your plan for today, on whether you want to finish today, and so on. So I cannot answer your question.
Okay, let me explain the proof. And then, okay. So what is it? Okay. So right. So certainly one implies two. So the point is that two implies one. The point is that you have this Tor condition. You want to go from that to condition. So we'll show that for all I, there exists I prime.
Just condition 2 says what? You say MI are flat. Is it?
No, sorry.
Is flat. It's not.
Sorry.
System is flat.
Sorry. Flat thing is flat as a process. So what we need to show is that these maps eventually factor through free modules. So, well, in fact, what you can always do is you can pick some free module F, some finite free module, which maps surjectively onto this, and then the statement is that this map eventually lifts over here. I prime is sufficient. Okay, so what does it mean to lift over here? Well, it's exactly saying that some x1 class vanishes. Right? It's saying that, I mean, the obstruction to lifting here is an x1 class from M sub I prime into the kernel of this map. Okay, so actually for this, it's enough to show that for all finitely generated R modules N, the colimit of x1 of M sub I into N is equal to 0. So we're saying that. So we're saying that the obstruction to lifting here is some x1 cost, but we can trivialize it if we go far enough. So in fact, this is the claim that we need if we want to prove. Um, all right. So this is what we're going to prove, and we're going to prove this using flatness process. Okay, so for this, we're going to use the following lemma. Let me just formulate it for Noetherian rings to make things easier, but you can formulate it in the generality as I mentioned. So let R be a Noetherian ring. Sorry, that's right. And let's say M and N are finitely generated modules. And let I be an injective is an injective R module. So then the statement is that our home from M into N into I is the same thing as M derived tensor over R comes from N into I. So the statement is that you have a natural isomorphism like this. Okay, so what is the proof of this? The proof is that this is going to be, well, the proof of this is basically a connectivity argument in that, so let me say the proof is that some sort of connectivity argument, and in fact, the point, it's true for any M, which is in a perf of M, which is pseudo. Because right, so what's the idea? Well, the key point is that okay, so you can approximate M. So this is true when M is perfect. This is true when M is free, and it's true when M is perfect. And then you write M as a colimit, as a sequential colimit of perfect complexes, which are getting more and more connected, which means that this R hom of M comma N, I mean, it keeps changing, but it doesn't, it sort of stabilizes in any range of degrees. And then sort of same thing over here. So you really need the fact that I is injective, so that this is in the heart, and so that when you form R hom into an injective module, it depends. Okay, so maybe let me not try to prove this, but let me just explain. Okay, then maybe time for me to stop. Let me just explain why this lemma will imply that. So. So proof continued. So suppose that well, let me suppose that colimit of R hom from M into N, M psi into N, is not concentrated in degree 0. So in fact, we just talked about x1, but in fact, we'll prove it for all the x. is has a non-trivial Hj. So suppose that this column has a non-trivial Hj. So then the point is that this, whatever this Hj is, it embeds into an injective module. So there exists a non-zero map from the colimit of Rhom from M sub I into N into an injective module shifted by minus j. So this is as a non-trivial Hj for some j greater than 2. So we're trying to show, again, this colimit of x1 is non-zero. Okay, I was just saying let's replace 1 by any j. If it's non-zero, then there's an embedding from this module into an injective module, which gives you a map in the derived category like this. So again, we're using that it's an injective module, so a map on cohomology automatically lives to a map in the derived. So you get such a map. Right, so what is that? So this is exactly, right, so this is exactly, so this is exactly inverse limit. So space of such maps, this is exactly I j of inverse limit of Rhom M sub I into N. It's exactly this. And so there's a non-zero map, and this lives in this group, just turning the colimit maps out of a colimit into a limit. Now, what we do is we use this lemma. So we use this lemma to say that that homotopy group is also this is also by lemma. It's I j of inverse limit I of M sub I derived tensor over R comes from N into. Okay, but now the whole point of flatness is that this is this derived tensor products. The whole point of flatness is that this tower in I is pro-zero. So this is 0. So that's a combination. So that's the proof. So that's the proof. That's a proof of this example, or of the special case, but in fact this argument works in general, of this result. So if you have a tower of finitely generated modules over an Ethereum ring, which is flat as a pro system, then that implies a pro equivalent tower of finite. The argument is to go through this next. So
somehow illustrate this without injective models. Because injective models are really so in the formulation statement there were no variable infinities. So embedding something into an injective model is a theoretical device which is technical, but can be avoided here because in the formulation 1 and property 2, everything is basically formulated in finite. Flatness is also condition formulated in finite terms.
That's
So it's just a desire, kind of. I'm sometimes afraid of that fear. Many in the 19th century, Kronecker had strong objections to Cantor's set. Maybe he was not flexible enough, but there was that maybe Kronecker was a little bit right. There is a way to avoid infinite orders.
Thanks. I think that sounds like a great idea. I'll try to think about it. I think struggle a little bit with this argument, but probably should try again, and probably should try to find a way without. Yeah.
IJ. Like to choose J maximal or something.
Well, we said that there's some j where it's non-zero, but then the point is that the pi j of this inverse limit of 0 by the fact that it's a pro-zero system.
Isn't that like when you say something is flat, it means that like the limit of the cohomologies is 0, right?
It's pro-zero. So the statement is that the pi j of this tower is pro-zero, and also pi j plus. It's another exact sequence.
Like that's what the pi j and the limit swap is.
Yeah, okay, so you're right. So there's a Milnor, in general, there's a Milnor exact sequence. It'll also be a lim 1 of pi j plus 1. Pi j plus 1 is also plus 1. But I think, I agree. It would be good to do this argument. So it must be possible to redo this argument in more finite
terms.
So I would do it. So it's already 6:30. So maybe let me just end by saying, so right, what was the point of all this? The point of all this was really to go back to the lecture a week ago. So then the point was that there was a Cartier duality. Well, the statement was that this group that shows up in sheared prismatization is Cartier dual, is group ind-scheme. Cartier dual to a very nice group scheme. And I think that's a fairly straightforward theorem to prove. Once you know that the group ind-scheme is actually of this form, it satisfies this Flatness. Because then you write down a map, and then you check its isomorphism by setting Q equals. And so the main thing is to actually check that that object is flat. And basically the point of all this, so your paper, you show the flatness of these various group schemes, show up as, and so basically the point was we can more or less, using this notion of flatness, and actually I think we do need this notion of flatness even without finding those conditions, we can more or less imitate the same arguments. So I think.
Thank you very much.
Thank you for all your questions and comments.
Are there any questions or comments?
So there was this statement about between the category of quasi-coherent shifts and group in scheme G and its Cartier, and between the category of representations of group in scheme G and the category of modules over the Accordion tree of its Cartier dual. So those statements. So suppose.
The dual statements for me, that will involve like quasi-co of
objects like BGA.
That will involve quasi-co of a object like BGA, but also objects like these. So actually, I think so. Maybe thought about this. So quasi-co of something like BGA in terms. So the example, right, so the example was that GA and GA have chart, Cartier dual in the sense. And so there's some relation between quasi-co of GA and quasi-co of GA at chart. And I think the same might be that they're literally the same if you put in co. But I'm not sure for quasi-co. This is sort of the opposite direction of the Cartier duality. Right?
So just so what was the point of so your first part of your talk was about the Cartier duality, and then so are you saying that to check that say the map from GM to GM sheared prismatized is profit, you need this more general notion. You need you need this proposition that you just proved.
So I think right. So maybe the application was to the kernel of to figure out, and the statement or the statement is that that's Cartier dual to in fact a smooth group scheme. And so in particular that uses some flatness, but so I think so following the arguments in Riffau's papers, the idea is that you can actually reduce to you can use this no potent criterion for flatness to reduce to the characteristic B hot state point, and then everything is very.
Are there other questions? So then the next Monday there will be a talk on the difference assumption by How Young. And let us thank the speaker.